everyone. Welcome to the Black Hole. Today we are gathered here to listen to Mohammad Haashir Ismail on the interesting subject of topology, which is a branch of mathematics that studies the global properties of various kinds of shapes or manifolds in general. So Mohammad Haashir Ismail has done his bachelor's in computer science from FAST, Islamabad, and also a bachelor's in mathematics from Virtual University, and his main interests are in mathematics, in particular geometry, and also in theoretical computer science. So today he will talk to us about this interesting topic and tell us about its history and its various things about it, I guess. So we will learn. And before starting the session, I will encourage you all to please turn your mobiles to silent mode. And also, when you want to ask a question, please ask for a mic and only ask your question in the mic so that the live audience can also hear your question. Okay, thank you. So let's welcome Mohammad Haashir Ismail.
All right, Assalamualaikum. All right, so before we actually get started, I'd like to know if anyone has actually heard of the term before in any sort of context. Anyone at all? What context?
Maths and physics.
All right, maths and physics. All right, you've heard it in physics.
Maths and physics.
You as well?
Pretty much in physics.
Pretty much, yep. All right, so of course that's my job. It's my task to introduce the subject, but does anyone have a vague idea what the word could mean?
I guess topo means shape in Greek or something, and logy means science or study.
Sort of. Not shape exactly, but rather position. So the study of, in fact, topology would literally mean the study of position or geometry of position. In fact, let's actually begin. First off, my apologies for having to erase this, but it seems to be a time-honored tradition. Right, they all seem to be colored over here. Yeah, there's no white chalks. Oh, okay. Okay, wait. There's white chalk. Yeah, oh, God. All right. So with all things effectively mathematical, we're going to have to start off with Euler. So a long time ago in antiquity, about 1700s or so, you had an old city known as Konigsberg, which consisted of a series of islands linked by bridge. All right. So one thing that puzzled people of the time of the era was, is it possible to traverse Konigsberg to essentially access each of the islands by crossing over every bridge no more than once? Now this baffled mathematicians of the era. Of course, though, Euler had actually proposed a solution in back in the day in a paper that he quite strongly titled On the Study of Geometry of Position. Now, why would he have done that? You see, this problem is not exactly one of distance in the first place. It doesn't matter how long any of the bridges are. It doesn't matter what the distances between these bridges are. It doesn't even matter how large these land masses are. The thing that makes Euler is the fact that he managed to reduce this problem down to just studying the relations between these islands and induced by these bridges. So to simplify things, I'm going to depict this as a graph. I'm going to use this circle here to represent this landmass, this circle to represent this landmass, this circle to represent this landmass, and so this to represent this. All right. All right. So what Euler did was essentially just boil down the problem, get rid of any sort of extra information, get rid of anything unnecessary, and then just look at it in terms of things being connected to one another. And he essentially proved in his solution that you can't really traverse every bridge exactly once if you don't have a situation where exactly two of these circles, exactly two, have odd degree. What do I mean by degree? What I mean is the number of ways you can enter or exit should be odd to be specific. Let's look at this landmass here. How many ways are there to enter or exit? There's 3 ways, representing these 3 bridges in abstract. Likewise here, you have exactly 3. Likewise here, exactly 3. And here you have 5. So what Euler realized was that the trick to figuring out Euler's solution is the fact that whenever you cross a bridge, why even? Why would evenness of these degrees matter? Because if you cross a bridge to get to another island, then to get off of it, you would need another bridge, and so on and so forth. You can't reduce an odd number. You can't essentially reduce. If you have an odd number of bridges everywhere, you can't actually balance out the edges you're traversing. Of course, though, this, however, does not lead us to the rest of topology as we would know it. In fact, Euler ended up working on something else much after. He worked on the study of convex polyhedra. I'd say this is where topology really takes root. Fairly basic cube. What Euler observed was that shapes like the cube or the tetrahedron, they obeyed this odd formula. If you took the number of vertices, subtracted from them the number of edges, and then added the number of faces, then for these shapes, it would always end up being 2. In fact, we can check it right away. Basic cube. How many vertices do we have? 8 vertices. How many edges do we have? 12 edges. And how many faces do we have? 6. 4, 5, 6. All right. Worked out. Ended up with 2. What about the tetrahedron? It's going to end up being the same situation here. You have 4 vertices. You have 6 edges. And you have 4 faces. Worked out for the cube, worked out for the tetrahedron. And so it's an interesting property. It seems to work. But remarkably, Euler could not prove it. Euler could not actually prove this property of his. It wasn't until we get to Poincaré.
Can I ask a question?
Sure, go ahead.
For this problem, so the explanation, if I understood it correctly, is that to be able to traverse all of the bridges exactly once, at least one of the nodes must have an even number of edges coming out of it.
Okay.
At least one.
At least one, sure, but in order to actually have some sort of path that visits every landmass while only visiting each edge once, as per Euler, you would need exactly 2 nodes to have even degree, which isn't met. You have one over here or by even degree, I mean it should have an even number of bridges connected to it. Over here you have 5 bridges, here you have 3 bridges, 3 bridges, 3 bridges. Reasoning
exactly 2 or more than 2 or exactly 2?
No, you need exactly 2 of these exactly 2 vertices in this graph to have an even number of bridges. So let's do it by, in fact, let's do something basic. After World War II, we actually did lose 2 of the bridges anyway in modern day Konigsberg. So pretend 2 bridges were lost. Now does such a path exist that traverses each edge exactly once and then touches each of the land masses? Well, sure. Exactly 2. Not quite. Which bridges were lost?
Or even if we just remove the central bridge, then also we will be able to traverse all of them exactly once, while keeping all the rest. So in that case, if you remove only the middle bridge while keeping the remaining, then you will have 2 nodes that will have an even number of edges coming out of them, and 2 with odd.
Yeah, in this case, we do immediately see the loop.
Yes.
Right. But again, that sort of stuff ends up delving more into graph theory than it does later into topology. The only reason this ends up being remarkable is the fact that there was no care of distances involved. Anyhow, Euler ended up demonstrating this result as well, but he could not prove it. It wasn't until Poincaré that we actually got to a formulation of this. Okay, but to be frank though, right, I'm just going to get into actual classical topology now instead of getting into the historical note of it. I'm just going to draw the familiar Cartesian plane. 2 points here. Are these points near each other? I mean, in one sense of the word, they're near each other. I mean, sure, there is some finite distance between them. One could argue they're near, one could argue they're far. But really, it's just a matter of your choice of scale or what do you consider far in the first place. The thing that makes the plane special is that if you end up picking any pairs of arbitrary points, I'll just drop one. Then you can end up calculating the distance between them. That we know because of Pythagoras already. So, what makes distances special? If you eliminate the issue of scale, or if you eliminate the issue of judging how near or far something is, you only recognize that there is a distance between them, then you realize that the only reason distances are special is because of the fact that, well, these two together inhabit some sort of region, or these together inhabit a region, these inhabit a region, these together inhabit a region, and so on. The only reason distances are special is because of the fact that by having a system of distance in place, you're basically allowing yourself to recognize what a region is. You can mark stuff, you can identify stuff, you can set up borders. So, what people like Frechet or Ries realized in the early days was you can actually discuss a lot of mathematics without needing to know what a distance is in general. So, what I mean by that is to say two things are near does not require a notion of distance. All you need to know is that two things are related. So, topologically speaking, these points are near if and only if there's some region that contains them, and that's about it. That's the essential jump between what you would have called metric to topology. Stop talking about distances, stop talking about lengths, and boil things down to whether or not they end up being commonly contained. Instead of starting with a distance and saying things are near because they end up being within some finite distance, you go the opposite way. You determine what points are near already, and then from that you can actually determine whether there is some suitable distance that recovers that information.
How can you say that two things are near without a notion of distance?
Simply by asserting the fact that they're near. That's the difference. It's a way of you're basically going about the idea in the opposite direction. You don't start off by saying, you don't say things are, topology dictates that you don't actually say things are near because of the distance. You argue that the distance exists because of nearness.
What does nearness mean without invoking the concept of distance?
Simply, it just means that they're related. You end up taking it on high as an axiom. So, what could be a good example of topological space? So let's start off with a basic example of what I mean by the issue of whether things are near or not. I'm just going to draw the classic real number line. Now, what do I mean by nearness in this case? In this case, what I mean by nearness or containment in a region is that if I have two numbers, could be anywhere, A, B, then there is some interval that contains them. That's what I mean by nearness in the case of the number line. All I need is the fact that they're contained in an interval. The rest ends up following through from just this. In the case of the two-dimensional plane, I say two things are near if there exists a ball that contains them.
Disk.
No, ball. An open ball, a disk, essentially a disk, yeah. Now, at first, it might seem like all we've done is basically fudge around with a definition and just make the problem make the issue of distances more complicated than it seems. But we've actually done something quite interesting. So, you might recall from calculus during college or basic university, you might have studied something called a continuous function. I'm going to just start with the old example of a real function from R to R. For instance, it could be something like f of x is equal to x squared. So the average student, when they're taught about continuity, they're basically told a function is continuous if you can draw its graph without lifting your pencil. That's the elementary definition used for continuity. In the case of x squared, for instance, barring any poor quality in drawing, one could try drawing the graph like this. I didn't have to lift the chalk. But this definition isn't really so formal. There's no way to what do we mean by lifting a pencil in this case at all? How would you define this thing, formally at all? So what you end up doing instead in elementary calculus is you say, you realize that by continuity, what we actually mean is suppose there's a point you want to look at, a special point you want to look at. What you mean by continuity, or the act of not lifting a pencil, is basically if I deviate from my special point by some error bound, some margin of error, then it must necessarily be contained within some region of error over here. That's what we actually mean by continuity. That essentially what you say is that if you're trying to judge continuity of a function at a point, or basically if you're trying to rigorize this definition of not lifting the chalk or not lifting a pencil, what you mean is that the graph of the function should approach where I expect it to be as my input gets to that point. I expect it to match vertically as I start to match horizontally. In a calculus class, you would have seen this in terms of epsilons and deltas. So what would a calculus do? It would have been stated something like this. All right, so what do I mean by this? What I'm saying is for any choice of vertical error, so error over here, there is some horizontal error such that whenever I am near A within my horizontal error, I'm going to be near f of A up to vertical error. All these lines I've drawn indicate is margins of error. And that's it. From this, you end up realizing that what we're basically saying is that a function is continuous if you're giving yourself the opportunity to squeeze in terms of error. So does that make sense? Now, of course, if you've done calculus, you realize this is a distance definition. This is a distance dependent definition. We're talking about epsilons here. We're talking about deltas here. You'll recognize this is just distance of real numbers. Here's the trick, though. Topology just does away with that notion entirely. Instead, in topology, a function f going from some decent set y, x, to some decent set y, where by decent I mean you have some definition of nearness. You say this function is continuous if a set near in Y corresponds to a set near in X. So in the case of X square, for instance, remember, these are essentially two real lines. So nearness for the real line I dictated was basically the interval, whether there's some sort of open interval. So to show that x square is continuous to show that x square is continuous, you realize this. Take f of a. Suppose f of a was contained in some interval. Could be arbitrary. This is a near set in Y or a near set on the vertical line. What does it correspond to? Or in other words, what sets on the horizontal line give you this near set over here? Draw the lines out, take the intersections. This interval here is just constructed by the intervals here and the intervals here. So this ends up being a continuous function without having to go through the hassle of constructing an epsilon delta proof. You just have to recognize where the intervals are coming from. Does that make sense? All right. Why would this matter at all? That's because some properties of the spaces you're studying depend exclusively on how they link to continuous functions. What do I mean by this? All right. I'm going to briefly cave in. Consider just the circle. Just the circle. Not the disk, just this path. How does one determine if this is equivalent to anything else? So for instance, how does one determine if this is all right, circle versus the disk. How could one discriminate between the circle and the disk? How can one determine if these are geometrically distinct? By the circle, I just mean this path here. By the disk, I mean the whole disk. Anyone have any idea what makes these two different?
Circle is one-dimensional and disk is two-dimensional.
Sure.
You need only 1 degree of freedom or coordinate to locate a point on the circle and 2 coordinates to locate a point in the disk.
Sure, that's a good way of looking at it. Any other ganders? Well, yeah, that's a good approach to it. You could talk about dimension. Or there's another thing. Consider a point living on the circle. And consider all the ways you could travel on the circle and get back to your point. There's only 2 ways to do that. You either go forwards or you go backwards. Now do the same here. You picture a point and you consider all the ways you can start at the point and end up back at the point. You could go here, you could loop like this, small loop over here. What you'll notice is that this space is funny in that you could deform these loops. What do I mean by deform? Take a loop here. If you try picturing a loop here as, say, a rubber band, and you end up having, say, a pin over here, and you have a rubber band. If here we're basically permitting the rubber band to actually traverse or to interact with this entire region, the disk. So naturally, your rubber band being allowed to travel over the disk, you can actually just bring it back here quite easily. Not so here. If you have a pin over here on a sheet of paper and a rubber band that's looping, and you're insisting that you want this rubber band to collapse back to this without actually getting off of the circle. You can't do that. No way to do that. In fact, on the 3-dimensional sphere, you can do the same thing. If I was able to somehow puncture a 3D sphere at a point, a globe for instance, put a pin, tie a rubber band around it, it's pretty easy to collapse that rubber band just to the pin itself. You can't do that with just the circle though. So what that means is this circle and this disk are topologically distinct. Or in other words, you can't In other words, there's some property about the property embedded here and embedded here that doesn't translate neatly. Physicists and mathematicians refer to this as the fundamental group. The circle is denoted as S1. S1 is just a fancy way of saying circle. So basically, all of the loops that live on this space just consist of the ways that you can wind around it. For instance, this loop is distinct from this loop. You cannot turn one into the other if you're picturing them as rubber bands, directed rubber bands. You can't turn one into the other without actually exiting the circle. Living on the circle, you're forced to view loops in this manner. On the other hand, with this space or this space, these have trivial fundamental groups. Or in other words, loops aren't really, there's no way to discriminate between any kind of loop. You can discriminate between loops here, but you can't discriminate between loops here. Why is it the case that these spaces end up behaving like this and this space does not? That's because of something in topology called connectivity. Or more specifically, simple connectivity. Essentially, what I've stated regarding rubber bands and pins and whatnot, that's just the definition of what topologists would call simple connectivity. If you can take any loop and then you can continuously deform it to a point, you have a space that's simply connected. Not so much with the circle over here. Can't do that with the circle. Does that make sense? So if you have two objects that have distinct fundamental groups, you don't have a nice way to say they're equal. What does a topologist mean by equal? What do I mean by this here? All right, circle and a square. Are a circle and a square the same thing? Yes or no?
No.
Why not?
Geometrically, they are different, but topologically, they are the same.
All right, care to elaborate?
Well, geometrically, they have different properties like different perimeters and different surface areas. That's what distinguishes them geometrically, but topologically, you can deform one into the other. So that means that they have the same topology. So they are indistinct topologically.
All right, pretty much it. In fact, I'll just draw a triangle here as well for completeness because why not? Okay. When you study shapes, normally you end up saying shape in school. You end up saying shapes are congruent to one another if they end up just being the same shape but flipped or about or rotated in a different way. That's what you mean by congruency in middle school mathematics. Later on, you start talking about similar shapes. You say two shapes are similar to one another if they just vary in scale. They're similar to one another. This notion of topologically the same, it's sort of more general than that. You say that they're the same if there's a way for you to somehow, without cutting or without gluing, turn one into the other, or if you can somehow picture one becoming the other. In the case of the circle and the square, it's actually fairly straightforward to visualize it. To turn the circle into the square, you could just take a series of bulges around these diagonals. We just bulge it outwards into the diagonals until you end up filling this completely. Of course, you've changed the area, you've changed the perimeter, you've basically made those properties different. But as far as topology is concerned, they are the same. In fact, what do we mean by topology in specific? It's quite easy to say that we mean geometry without distances or geometry without angles. What we mean is, in fact, the study of things in geometry that are left unchanged if you allow yourself to not cut and not glue. Do anything else, but you're not allowed to cut or glue. If you want to collapse a loop here, you're going to have to cut it. You're going to be stuck cutting it. But because we forbidden cuts, you end up getting this result that you have to look at every loop distinctly. Sure, one loop could be slower than another. That's a different matter. But qualitatively, because you don't care about how fast a loop is just a loop.
One question, do knots in 3D space have the same topology as S1?
Okay.
Like trefoil knot or something.
All right, you've asked me what a knot is, all right? We're gonna have to now define a knot. All right, so a knot just ends up being some way to embed a looped object into three-dimensional space. For instance, this ends up being, the circle is just the most basic knot you could consider in 3D space. Then you have the common examples like the trefoil knot and whatnot. So what about
basically all of these knots, the traditional knots in 3D space, like trefoil knot, etc., all of them are like topologically the same as S1, right? The circle.
They're embeddings of S1 into R3, but they're also distinct in the sense that they're distinct in the sense that they have certain invariants that allow you to discriminate one knot from another. The knot theory ends up being a fairly advanced study of topology that ends up going.
Them into 3D space.
Yeah, you're just mapping the circle into 3D space.
They are not the same as S1 because S1 is just the unknot, what is called the unknot, the simplest knot that is just a circle. And then the more complicated knots have different topology because they have different topological invariants associated with them. Mm-hmm. Yes.
Yeah, I don't want to get too far in knot theory, but for instance, knots have polynomials you can build out of them by studying their crossings and whatnot. So, no, they end up having very distinct properties. Topologically speaking, these end up being spaces of the same sort as well. In as far as if you have these fixed reference points, every loop is contractible to a point again. Likewise here. Likewise here. So the study of objects using the loops you can build on them, although a powerful method, doesn't really discriminate as easily between objects of this sort and this. Loops end up being they're a good discriminator, but they're also limited. You can't discriminate between shapes that are different to some element like this, like geometric stuff like if you have changes that occur due to length, you can't discriminate between them as easily. But I could easily discriminate between a donut and this. How could I discriminate between this and this? This loop doesn't contract. Same issue with the circle. If you ended up putting a knot here, rubber band, and then you surrounded it with two circles and said, try shrinking this band down. This ends up being a forbidden region. So there are some loops here that end up being distinct. This stuff, though, ends up being more along what we would call algebraic topology. That's just one branch of it. The other stuff, which is what physicists would find fairly interesting, ends up being what you would call differential topology. All right. One can talk about curves in 2D. One could talk about surfaces in 3D. How does one generalize them? How does one generalize the idea of a surface or a curve? That ends up stemming from topology with what we call, and what you might have heard sometimes, a manifold. You guys must have heard it considering you're physics people. All right. All right. So if one wants to generalize the study of surfaces or curves, objects of this sort, it's immediately obvious. It's not possible for us to visualize 4 dimensions as coherently as we could 2 or 3. No, there's no way to actually studying them just by drawing it out. So you end up having to resort to different tactics. So with mathematics, you end up constructing this definition, that of a manifold. And the neat thing about them is that, just as you might recall from calculus, you could define integration on lines, you can define integration on surfaces. The neat thing is you can define integrals, or you can define an idea of integration on a manifold or on a general surface. Those of you who have taken a course in multivariable calculus might know of things like Stokes' theorem or Green's theorem in the plane. But if you're a geometer, you only look at them as one thing. Pretty much just a fancy way of saying small changes on the outside. It's just a fancy way of saying changes on the outside are the same as the sum of small changes on the inside. All right. What could one discuss beyond this? You know what? How about this? Everyone at some point has heard of this result from high school or whatnot that take a polynomial, say x cube plus x square plus 2, whatever, general polynomial. You might recall from high school mathematics or college level mathematics that any sort of polynomial admits something called a complex root. What I mean by that is such that fairly standard result, must have heard of it in high school. Any polynomial has at least one complex root. How could one prove it? I mean, Gauss and co actually did prove it, but any ideas how one could show such a thing? Well, topology actually lets us figure it out fairly trivially. I'm drawing now what's called the complex plane. So, real, imaginary. If I have any polynomial, it's going to look any polynomial with okay, one thing to keep in mind is I will, okay, hold on. If you divide by the coefficient, if I divide by this leading coefficient an, it doesn't really change any place where it doesn't change the location of any potential zeros. All it does is determine the scale of it. So I only need to consider polynomials of this kind. Any polynomial of degree n just looks like this. It's some term zn plus a bunch of other terms. So for instance, this ends up just being x cubed plus a bunch of other stuff, x squared plus 2. Polynomial. Now, the interesting thing is Zn. If you pick a very large number, if you pick a very large complex number, then what happens to the polynomial? Okay, real case. X cube is clearly for a very large number, say 10 million or whatnot. X cube, or 10 million to the cube, will be far bigger than 10 million squared plus 2. Yeah, it dominates. This is a dominating term. So in other words, if you pick a very large number in a polynomial, the thing that dominates will always be this leading term, the term of highest degree. The same is true if you talk about a polynomial if you talk about a polynomial with complex variables. If you swap out the x's with z's and you're interpreting z as some complex number, same thing happens. This dominates. Except in the case of a complex number, if I pick, this is the origin. I start off on some very large circle. This circle could have a radius of, say, 10 to the 10 or something. For example's sake, if you just considered the real numbers, then then looking at it this way, you would immediately realize the only thing that matters is the leading term. Everything else ends up just being paling in comparison. In the complex case, this is the same as saying I'm talking about a circle here. Now, so what happens is Zn all right. Take a polynomial and I'm just going to travel around a fixed circle, a very large circle. What happens is what Zn basically says is if you have a circle that loops around the origin once, Zn will force it to loop around the circle n times. You can interpret a polynomial that way. So we started off with something that looped around the origin n times. Now let's pretend this polynomial does not have a zero in the first place. It doesn't have a single complex zero. What that means is that no matter what value you substitute, or in other words, if I try squeezing down this circle, it's not going to hit the origin. That's what the argument basically says. Now, I started off with a very large R, I get a big circle. Now, what if you start off with 0? What if you end up taking R0? What if you just talk about a point? So there's two extreme cases. You either have a circle on the looping, or you have some non-zero point. With me so far? We have something that loops around the origin n times, and it becomes something that loops around the origin no time at all. A point doesn't loop around the origin. So in other words, if it did not have a complex zero, if there was no zero of this polynomial, then you would, by shrinking this radius, you could get a series of smaller circles that eventually shrink to this point. But try picturing it for yourself. There's no way to shrink these circles without hitting the origin. Can't do that.
Where did that point come from?
Oh.
Point.
Oh, you just consider a circle of radius 0. We dictated that this is a polynomial with no zeros, no roots, right? So that means that for some, say, f of 0, by hypothesis, that means f of 0 is not 0, right? But then it has to be some complex number. Could be a point here, could be a point here, could be anywhere. So on the one hand, you have a very large circle representing one extreme, and then you have a single point representing the other extreme. But you can't possibly. So similar to the issue of trying to deform a rubber band tied on a knot, there's no way for something revolving n times around the circle to become something that doesn't revolve around the circle at all without hitting this at some point. Can you picture a way to collapse this loop without crossing this? Can't. It's going, no matter where this point is located, a very large circle will have to hit the origin. And that ends up being a very elementary proof. That ends up being a fairly elementary proof of, or at least a proof sketch of what you would call the fundamental theorem of algebra. Everyone's essentially read this in high school at some point.
So this only proves that there must be at least one
complex zero
solution at least. It doesn't prove that there must be n if the degree of the polynomial is n, right?
No.
Because that's the fundamental theorem of algebra. That there must be n complex roots of an nth degree polynomial. So this only proves that there is at least one, but So this
Now,
is
to my recollection, what you're talking about isn't actually the fundamental theorem of algebra, but what you're talking about is the completeness of the field C. That would be a different result.
I don't think so. I think
What's the notion of topology in that case?
Oh, in what case?
What's the notion of topology?
Here. The idea of topology here is that you make an argument without having to explicitly use any sort of calculus trickery. What I mean by that is that the notion of topology here is you just talk about things in terms of a loop. We started off with basically for a moment talking only about the leading term of a polynomial. You can immediately recognize that it's an argument of loops. You can insert a very large loop, and you can then dictate a point. You get two extremal situations, a very large loop and a point. And then the idea is if you continuously try shrinking a loop without bothering with the notion of a distance, you end up stuck at this fact that you have to hit zero at some point. It's topological in the sense that it does not deal with any analysis, or it doesn't deal with any notion of what a derivative is or and it's not algebraic per se in that we're not talking about some sort of structure. Like for instance, in high school mathematics, you're introduced to the first notion of structure, which is a group, or you might eventually talk about a ring. We're not talking about a group or a ring. All we've restricted ourselves to is the study of it from the view of loops. So geometry without explicitly forcing a distance. Does that make sense?
Actually, we are going to find out the optimal range of the point with that optimal.
Let me give you the mic.
And I'm just figuring out that actually we are going to find some type of optimal range of that loop to that specific point. We can relate that.
Not really an optimal range.
Nearest optimal range will define the nearest of the points in topology of notion.
Not quite. Not quite exactly, because if we're talking about an optimal point, then there's the issue of actually finding what that optimal point is and whatnot. We're not really dictating we're not dictating what it is, we're not dictating where it is. We've essentially only asserted that it must exist.
Okay.
And we're doing so without being very specific about how we're getting it. All we've spoken about is that a very large loop cannot collapse to a point in this plane without hitting the origin at some point. Or a loop or something that loops around the origin n times cannot loop onto a point which loops no times without hitting the origin at some point.
Essentially saying is there's going to be at least one zero.
Yeah, there's going to be at least 1 0. Fundamental theorem of calculus. Fundamental theorem of algebra. Calculus is a different thing. Yeah, it's a fairly elementary way of introducing it without having to talk about things like fields and whatnot. All you have to know is what happens to a loop. So, you have a good question though. What do we mean by topological notion? The issue is it is a tricky question. On the one hand, you have set topology, which is just, we talk about things in terms of sets that define nearness, as I was mentioning at the start. On the other hand, algebraic topology, they don't bother with the set work at all. Instead, they're just concerned with what happens to loops that live on a space. And then you have the differential topologists, which are a different breed entirely. They start talking about things in terms of smooth maps. They introduce notions of calculus into the mix.
Okay.
So it's quite difficult to describe in general what we mean by topological notion beyond dictating that, we're not too concerned with what a length is. Smoothness just means you're forbidding sharp corners from being introduced. An algebraic topologist is concerned with things like holes and whatnot. And a point set topologist is more concerned with whether you can actually say two things are near in the first place. This is topological in the sense that we've only talked about loops. In fact, topology is actually now one would bother. Okay, besides the physicist, one might ask why bother studying topology at all. Topology ends up being important for a good chunk of domains. What I'll end up mentioning very briefly is its importance in computer science. So, I believe it was the 80s when two computer scientists, Haashir and Shavit, essentially used algebraic topology, or the idea of a fundamental group, to basically talk about something called asynchronous computing. So you see this all the time with your phones. Your phones can communicate with each other. Your phones can message each other. Now, there are some tasks that require your devices, your computers, your phones to wait on each other. For instance, when you're on a phone call. There are some tasks that don't. For instance, if you're on instant messaging. Computing ends up reducing it more broadly into tasks that have wait times and whatnot. What was shown in the 1980s was that certain tasks, certain computer problems, PC over here, PC over here, PC over here. Pretend these boxes are PCs and the lines just represent the network links between them. So for instance, if this guy's working on something, he might need to wait on a result from this PC and whatnot. What Haashir and Shavit showed was that if you had a specification of computers in this sense, that one must wait on another, one must wait on this, one must wait on this, and so on and so forth, and you only describe this in this manner, then you could determine whether the problem can be solved without a waiting time or with a waiting time based on a certain topological property that it would correspond to, based on a certain geometry you could build. It's a bit tricky to get into because apparently their paper is actually 88 pages long, which breaks the notion of a modern CS paper. But they actually did systematically study the issue of computers that communicated distances using topology. Likewise, in fact, you mentioned optimal ranges. When you're studying optimization on weird spaces or on weird domains, for instance, if you want to optimize on something that's jagged, you would use topological methods. If you want to study things in terms of locality, if you can't talk about something globally but you want to talk about it in a small range, you would be using topological notions.
Is convex optimization also covering that?
Convex optimization? Oh, absolutely. Convexity ends up being one of the convexity ends up being, in fact, a lot of interesting topology ends up being due to convexity of spaces. Convex optimization does, to a good extent, have links to topology. In fact, if you open up a basic topology text like Munker's, for instance, you end up using the trick that some spaces are convex to basically get topological results for them. So, for instance, consider the real numbers, just R. You could use the convexity of R to show that every point, that between any two points, there is a path that links them. You end up exploiting convexity there, and vice versa. Some properties of convexity are nice enough that you can use them to prove topological results in certain cases. Other cases, you can get properties on convex spaces by reducing the general property. But convex optimization is fairly linked to topology.
Because actually, in a simple words, you can say that convex optimization, you have to deal with nearness to the points to get the desired optimal solution or that can nearest point, desired point.
Yep.
By
In fact,
getting the some difference to that of epsilon value, less than value, steps as well. So
right.
you can relate that.
Right.
Concept.
Right. That's essentially how it works. In fact, the whole point is topology started off as basically you talk about epsilons and deltas, you talk about distances, and then you realize some properties don't necessarily depend on distance. Continuity, for example, is not really distance dependent. It only depends on your idea of what do you mean by near. So, but again, back to the quadratic. You can say x squared is continuous without having to do an epsilon or a delta. All you have to realize is that an interval over here corresponds to two intervals over there. That's continuity in a topological way. All right, anything else on anyone's mind?
How would you define a topological manifold?
All right. Okay, so if you want to generalize the definition of a surface or a curve, you're going to need only two things. One, you need to know what do we mean by something being Hausdorff. So, okay, suppose you have 2 points in the plane. How do you know that these points are different?
Different coordinates.
All right, they're different coordinates. But a way of saying that these are distinct points without having to appeal to coordinates or without having to appeal to numbers. There is at least one circle that contains this, but not that. And vice versa, there is a circle that contains this, but not that. So roughly speaking, that's what we mean by something being Hausdorff. If you're in physics, you might have heard the name before as well. It just means you can discriminate 2 points by showing that there is I'm being imprecise with my language here. But you say something is Hausdorff if you can say that points can be separated or discriminated by two sets, distinct sets. And then you need to know something called second countability. What we mean by second countability is that your whole space, or essentially all of the near sets, your notion of nearness, can be described using something called a basis. What do I mean by a basis? What I mean is, okay, I'm going to start with R again as an example. And by the bases, I mean all of the intervals. It's a basis in the sense that any possible interval you could build, or any open set you could build, yeah, this basically covers all of it. You could represent it in terms of the unions of this. You could represent it in terms of the finite intersections of this. That's what we mean by a basis. Or in the case of the plane, you end up using the disks as your model of bases. So essentially, any point can be represented as any region, any valid region, for instance. Consider this region. It can be represented as the union or as the result of several circles, possibly arbitrarily many, but you can represent them in terms of circles. That's what we mean by a basis. So if you have a basis that represents your whole space, not just the regions with the regions near a point, but the whole space, you have something that's called second countable. So a manifold then ends up being a topological manifold, ends up being a topological space that is Hausdorff and second countable, but it looks at a point like the plane, the line, so on. In fact, I'll actually get more specific. I'll give you an example. Consider the sphere. Consider just one point on the sphere. If you zoom in, it starts to resemble a plane. If you consider a circle and zoom in very greatly, consider you have perhaps the strongest magnifying glass you could imagine. It resembles a line. That notion of resembling a line, a plane, 3D space and whatnot, that is what essentially makes something a topology. That is what makes it a manifold afterwards. That it should look locally Euclidean. So by manifold we mean Hausdorff, second countability. And when you zoom in, it should look like one of the spaces you're familiar with, a line, a plane, or 3D space. Does that clarify it?
Should the vectors be linear independent or dependent? In topology sense, the vectors should be linearly independent or dependent.
In what?
For resemblance case. Linear independent case or linear.
Okay, no. You don't need linear independence exactly. What you need to show that, what you actually just want to show is that there is a special map on some nice set that actually maps into Rn for some n. And you need to show that for every point it's the same n.
I'm talking about in a sense of vectors sense, 3D vector.
You don't really need
high dimension vectors.
No, you're not going to
the high dimension vector, and we want to assess the topology of two vectors. Then those vectors should be linearly independent or dependent.
By two vectors, do you mean the space?
Case,
do you mean the space spanned by those two vectors?
Yes.
Okay, the span of two vectors. Not really. You wouldn't need to consider. I mean, perhaps you would if you have a set of vectors, potentially linearly dependent, potentially linearly independent. Then you're aware that at the end of the day, they'll just span some sort of linear space, right? By definition of span, it just consists of all of their linear combinations.
Yes.
So all that would matter in that case, is whether you could somehow relate that to relate that to some other Rn. For instance, does there exist a mapping between that's about it. Does there exist a mapping that links the span of your vector set to some coordinate space? If so, then what does that mapping look like? Does that mapping have an inverse? Is that mapping itself continuous and its inverse continuous? And then from that, you could actually deduce, based on what sort of space it closely resembles, you could deduce the topological properties by instead looking at the other space. So for instance, if you had a bunch of vectors to which there existed a natural mapping, for instance, suppose you have 3D space, and you have two vectors linearly independent, and of course together they span a plane. Then that plane has a reasonable embedding into R2. So of course, then you could topologically look at it as just R2.
We're just figuring out the coordinates from that vector space. I'm getting that point.
Yeah, you could reasonably parameterize it.
Parameterizing.
In fact, parameterization is one of the fundamental tools in differential topology. Except instead of talking about just two vectors, you might talk about the tangent vectors on a manifold, or for instance, you take this circle here, you start talking about the tangent over here, you start talking about tangents over here. Parameterization actually just means that I can somehow turn this space I can interpret this space in terms of Rn for some n.
Transformation.
Yep. Doesn't have to be linear necessarily. It just has to, depending on my context, it should be continuous or at least continuously differentiable or continuously k times differentiable. Depends on context. I might expect more properties of it, but it doesn't necessarily have to be linear. Right. Anything else? All right, that about wraps it up then.